Muchas gracias por venir a todos ustedes. Bienvenidos al segundo workshop HPC UD 2017. Para el doctorado en Ingeniería de la Universidad Distrital Francisco José de Caldas, es un orgullo y un honor contar con la presencia de todos ustedes acá en este evento, orientado a la comunidad académica interesada en temas de computación de alto desempeño. Agradecemos enormemente su participación e interés en estas temáticas. El workshop que tenemos a continuación se llama Workshop on Machine Learning Using Intel Architecture. Estará enfocado en presentar los principales conceptos relacionados con redes neuronales y mostrar la aplicación de técnicas HPC para definir y entrenar estos modelos. El conferencista invitado es el doctor Rafael Méndez de Oliveira, investigador asociado al Centro de Computación Científica de la Universidad Estadual Paulista, UNES. El doctor Méndez de Oliveira tiene el doctorado en Ciencia de la Computación del Instituto de Matemáticas y Estadística de la Universidad de Sao Paulo, con énfasis en inteligencia artificial. Cuenta con más de 10 años de experiencia en el desarrollo de software en proyectos relacionados con Grid Computing, Cloud Computing y Big Data. El doctor Méndez de Oliveira es traído a este evento gracias al doctorado en Ingeniería de la Universidad Distrital. El doctor Méndez de Oliveira, doctor Méndez, thank you very much for coming. Columbia Global University. It's our pleasure to have you here. Y sin más preámbulos, demos inicio, so we can start. Thank you very much.
Okay, thank you. So, hello everybody, and just to make one thing clear, this workshop is going to be presented in English, but feel free to ask anything in Spanish. We have people that can translate. So, yeah, if you have any doubts or any thoughts that you want to share, you are free to interrupt me at any time. Let's make this as more interactive as we can. So that's a good thing of having this workshop at the end. Another thing is that I'm not going to give this presentation just by myself. I brought a colleague from Brazil. He's working with us. It's Julio, his name, and he holds a master's on. Okay, it's from the IEA Institute in Brazil. Okay, masters, especially in the field of machine learning in neural networks. So the expert here on machine learning, I'm giving part of the talk, just like the introduction and also the hands-on. We're going to split the talk into two parts. We're going to talk in general about neural networks and the concepts, just to make sure that everybody understands the same concepts the same way. So, in the next part, we're going to do some programming. Okay? So before you should ask, hands, those who have already worked with Python. Okay. Yeah, tough problem. MATLAB. Okay. So the rest of you, what do you work with? C. So yeah, in this workshop we're gonna program in Python, which is a really good thing because in machine learning, that's what most of the people are using right now. So most of the frameworks that you are gonna heard of, or you're gonna hear of, or you're gonna read about, most of them are gonna be written in Python. And why Python? Because it's quick, it's easy to use, and it's really nice to publish. Those of you who are not familiar with Python, don't be scared. It's gonna be really easy for you to grasp the concepts and then write a few lines. It's not gonna be that hard. So yeah, that's a good stuff. So as I said before, feel free to refer to me at any time. Okay? So just a couple explain about the Brazilian institution where we work for. So it's the São Paulo State University. It's a big one in the state of São Paulo, which is the state with as much people as China if China was really small. So yeah, we got lots of people there. And we there have a university with several campuses distributed all over the state. Okay, so we have kind of a distributed university, which is really, really nice because we have to learn what it is to collaborate among all of our institutes. So we have like 23 campuses spread all over the state. So it's a nice place to study and also to work. The inauguration of the university was in 1976. Sorry. So it's quite old in Brazilian standards. So it's a very traditional university. Okay. This is about the university. So we work at a computer center called the Center for Scientific Computing. And at that place we have training infrastructures. One is called Grid Mastery, which is a grid that provides for our researchers from all over the states. And also we have another one called the SPRACE grid. SPRACE stands for São Paulo Research and Analysis Center, which is basically a tier 2 CERN, tier 2. I mean, I can only assume that all of you heard of CERN and the LGC. Okay, Collider. So yeah, we have a close partnership with CERN, and the LHC data is stored and processed in a tier-based architecture. So it's more or less like an onion. You see, you have the tier 0, which holds the data from all of the sensors at the collider. Then we have the tier 1 that holds replication of those data, and they're usually placed in very large data centers. And we also have the tier 2, which is mainly research institutes. So we store, a percentage of the data collected at the LHC. Actually, more specifically, we have the F5, FC. Okay. So more specifically, we are connected to the CMS experiment. I mean, you guys know the LHC. It's 20 kilometers ring that sits in the border of France and Switzerland. And we have 4 experiments there, 4 detectors. The 2 biggest ones are ALICE and the CMS. We work closely to the CMS experiment. So we hold this data there, and we serve computer power for researchers to make analysis on this data. So you can see where our interest in machine learning and big data comes from. Okay, so we have a background on HPC. We were the first cluster in Brazil to serve computer scientists and other related areas from all the country, and then we had to narrow our scope and just serve computer power to the state. So, yeah. Also, other than that, we still have some other collaborations with other institutes like Caltech in the US, for lab also in the US. So we are based on a theoretical physics institute. Okay? At our campuses, there's no computer science program. So yeah, so there are a couple of computer science programs in other campuses, but ours is just for physics, which actually for us it's better than sitting on a computer science program because we try to develop solutions to real problems. I mean, real because we're talking about theoretical physics. I don't know if it's really real or not, but not going to talk about that right now. So yeah, this is some pictures of the place that we have. Is our data center. Okay, go ahead. And just a few numbers about our computer power. At the greediness, we have like close to 80 teraflops, and also 300 or 400 terabytes of data. Okay, we serve computer power for over 68 research groups, and then there's some like 377 researchers. Okay, the Space Grid, the other one that I said that I talked about, is the one that stores data from CERN. This grid in specific, it doesn't really have lots of computer power, so it's just a 15 teraflop computer. But we have a lot of data, a lot of storage. So we got like this data, that I think it's kind of old. The number now is going to be like closer to petabytes. So it's a lot of data. So the data there stored is mainly about projects working with dark matter. Dark matter discovery is that FEI collision. Okay. Infrastructure. So we are really happy to say that we have the best interconnection between all Brazilian institutes. Okay. So we have a dedicated 100 gigabit link that connects us from São Paulo to the US. So bandwidth is not a problem for us. Okay, so yeah, with data, we work with HPC. That's why lots of they reach us for making some. So we work right now with Intel mainly. I mean, we have other partners, but in the field of HPC, solution Intel, and also a Chinese company named Huawei. Now, about the Intel project, that's the project that brought us here. Okay, so we have a project with Intel. We built the Center of Excellence in Machine Learning this year, so it's kind of new. I mean, we're still hiring. Actually, I'm going to talk about that at the end. Some of you want to come and work with us. We are hiring. We work really hard for people. So the idea of the Center of Excellence in Machine Learning is to help mainly the physicists that are located at our building with their problems, okay, related to those experiments that I talked to you about, and also to provide some consultations to external partners. Okay, so we now have some collaboration with some financial institutes in Brazil. And most of the banks, we have some kind of collaboration with them. We provide consultations on machine learning. Okay, so that's where we come from. So why are we here talking to you about machine learning? So I'm going to talk a little bit, just make a quick introduction on neural networks. Please raise your hand who has ever worked with neural nets. Okay. who has ever heard the term neural network or deep learning or something like that? Talk to me, please. Okay. So we are gonna have to explain some concepts so to make it easier for you to grasp the idea of neural networks. So, research in neural networks, it became really popular with the first models that were built of the brain. I mean, the brain can be modeled, can be simplified. You can build a simplified model of the brain in mathematical terms. So those models, they start to rise in, I don't know, I guess the 40s or something like that. And once someone figure out how the brain works, I mean, we don't know it yet how it works, but we have some vague idea of how it works. I mean, we understand the mechanics right now, so we're not really sure which parts of the brain are responsible exactly for what. I mean, the brain holds a really nice feature, which is plasticity, which means that if you lose one part of the brain, then another part takes its responsibility, and you can live without part of your brain. Actually, there's one specific case of a British girl that she suffered from a disease when she was little, when she was a baby, and then they have to remove half of her brain. And thanks to plasticity, she lives a fully functional life. I mean, she had to relearn some and lots of stuff, but she lives a normal, healthy life. So yeah. So the brain suffers from this, which relates really, really much with what we are discussing right now, which is the synergy between machine learning and also HPC. As most of you could have heard, HPC is about parallel computing. So the idea of having these parallel circuits responsible for receiving some input and also producing some output, it's really close to the brain model that we have right now. So neural networks, they were born to work pretty much the same as we understand that the brains work. So the basic unit that we have there, basic component, is called the neuron. Okay, human brain holds about 86 billion neurons, which is, I mean, I'm not from the biology, okay? So I learned a lot in neural networks, and for once, there's not just one type of neuron. Didn't know that, but there is not just one. And actually, you have neurons that they spread through all your body. Okay, so they interconnect with your nerves, and then they bring all the inputs from your foot to your brain. And the number of connections that you have between the neurons is huge. It's 10 to the 14 or 10 to the 15, which is huge. I mean, you can think of them as really, well, it's a net. So it's a network. I mean, the interconnection is a net. So here's a picture, a really basic picture of a neuron is. So it basically has three parts that I'm going to talk about. But as I said, not a biology. We have the dendrites, which is responsible for receiving the impulse from other neurons. We have the nucleus, which is responsible for discerning this impulse and deciding whether or not to propagate this impulse. Okay, so the impulse comes from here. Here you decide whether or not you're going to forward the impulse, and the impulse is forward using the axon instruction. Okay, so here we have determinations where they're connected to other dendrites, not connected physically, but the impulses uses chemical-based communication tunnel. Go ahead, say.
Neurotransmitters.
Yeah. So yeah, as I said, the brain holds a really high level of parallelism. And many of the others, they agree that that's why the brain is such a powerful machine. I mean, you can only tell that you can only see when you look at a picture of someone that you know. It takes you half, I don't know, I guess around 300 milliseconds to identify a known face in a picture. And for a computer, that's really, really hard. I mean, only now you have like acceptable models that can actually tell what is a person and also what is not a person in a picture. And you can do that as soon as you're born. So yeah, the brain is a really, really amazing, most complex system that we can imagine of. It's the case that I don't know, 9 years later, we still don't know how it works. So yeah, probably we never will. So going forward on the simplifications, okay? As I said, I'm not a biologist, so whatever I said, it's gonna be like a really shallow introduction. And now we're simplifying even further, trying to make a mathematical model of what a neuron is. So here we have a picture which is we took from the Stanford Computer Science course on machine learning. It's a really nice course. I recommend to any of you that wants to really know what is machine learning, actually what is neural networks. But yeah, moving on. So this model tries to make it, look like a neuron, so you can actually identify which region is responsible for what. So in the picture we can see the dendrites, okay, which you guys must remember is the part of the neuron that's responsible for receiving the, I'm gonna call it signal right now, not just symbols, but let's call it signal. Okay, so this is the part responsible for receiving the signal. This is the part responsible for summing all of the signals. Okay? Because a neuron, as I said, we have a huge degree of parallelism. So we don't receive impulse for just one region. Okay. So I mean, there are some. Okay. You receive impulse from several regions. I mean, from several nerve terminations, and you decide whether or not this impulse should be propagated. This signal should move on, and that actually makes sense. I mean, if you are facing a dangerous situation, I mean, suppose you are inside a fire, okay, and then you have the nerves in your hand saying that it's really, really hot, okay, then you should take some action based on that. But if you have impulse coming from other regions, I mean, your hands, your feet, I mean, your whole body says it's really, really hot, then this impulse here should be much, 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 much more higher. I mean, the probability of the impulse is going to be really, really high. So, yeah, that's the idea of having several inputs and then summing them out, whether or not I'm going to propagate those. Because sometimes the inputs are not really that big. My little finger says it's hot. Okay, I can live with that. Don't worry, no need to make an alarm. So, yeah. So we took this idea of a neuron, okay, and we are going to imagine that this is our basic computation unit. Okay. The picture, the previous picture. The thing is, each dendrite has a weight associated to it. Then there are some impulses that are going to be of higher precedence than others. Okay, so this impulse can be of much more value than this one. So that's why we use the weights. Okay, and so for people when they talk about your really, really complicated thing, I mean, it's gonna be something like magic. The first time I saw one working, I was like, wow, how can you do it? Okay. First one I ever implemented, it recognized handwritten digits. I mean, you wrote like 1, and it said that's written 1. And it took like, I don't know, just a couple of lines code. And I was like, well, if I had to implement this using a fixed computation function, I mean, if I had to write a for and then a lot of if then else statements, it's gonna take forever for us to learn how to do that. So using this kind of abstraction makes it easier to solve problems that fixed computing cannot do it really, really fast. Okay? So guys, if you have any doubts, anything you want to write, go ahead and start. So when we talk about neural networks, and then most of the people, they talk about the learning procedure. It's, wow, something you make a computer learn. And it sounds complicated, right? I mean, look at our assumptions. We are simulating a brain, and we are simulating the learning procedure. But actually, it's not. I mean, the learning procedure is nothing more than just guessing what these values are, which are our weights. Okay, in the previous picture, as I said, we have the weights. Yeah. The only thing that we have to do during learning is understand values are. Okay. So then we use some fairly complicated math to do that, but they are really old procedures most of the time. I mean, the main procedure used to perform this training thing is got to come up just like, I don't know, in the 50s or something. So the procedure is really old. We have some tricky mathematics, but the idea behind it is really, really simple. I mean, it's really, really simple. As I said, you have to just figure out what the weights are. Okay. And then how do we use these models to solve problems? I mean, the first abstraction that we have to do is we have to be able to understand the problem that we're trying to solve as a function. Okay? So we have inputs, and we should have some outputs. Okay? Most of the time, we are not talking about one function. We're talking about a really complicated function. Perhaps that one that we don't know about. Most of the case, we don't really know what this is. Because I mean, if you want to predict what this is, if I tell you, all of you will be able to tell me what's the result of this function, assuming that x is equal to 2, right? But if this guy here is really, really, really complicated, then most of you are not going to be able to understand it. Okay? So we're trying to make an approximation machine that kind of works like this guy. This guy for most of the cases. We don't really know what this is. Maybe it's a really, really complicated equation. But we want to approximate the behavior of this equation. Okay. So the idea of neural networks is trying to build a machine, an approximation machine, that has a behavior very similar to this one. It's never going to be the same behavior as this one. I mean, because you never know, most 99% of the case, you don't have all the data in the world. So you cannot say that you really know this guy, but you can make an approximation based on what you got so far. So that's the idea of using neural networks. Actually, that's more machine learning thing, but we are going to use the idea of neural networks here. So we're going to do something like this. It's a function of now the inputs, the data I have, and also the weights that I'm going to calculate in the network. So the learning procedure is going to take the input, find good values for the weights, so that you have a good approximation of this guy. So that's the basics behind the learning procedure of neural networks. Okay, the architecture of the thing. I said before that the principal component that we are going to have is the neuron. Okay? So some of these units are going to be computing units. I mean, some of them I'm going to use to make computation on. I have to the nucleus of the neuron. And some of them I can just call input. Right? They don't have to do nothing. They just connect to my data set, providing the data to perform the training and also the inference using our model. So it looks like this. Here we have what we call, another abstraction that you have to keep in your mind is that we separate, actually we put together some of the neurons and we call this aggregation a layer. Okay? So when you look at like this, it's going to be like a graph. Some of you have heard of graphs, which is structures that connect nodes, and the nodes are connected using arcs. Okay? So these neurons, they are aggregated, they are put together inside a layer, and we have basically three kinds of layers. We have the input layer. This has no computation in it. And we have the other ones, the hidden layers and the output layers, and this they hold computation inside of them. Okay, why do we call this hidden? Because it's not the output. That's the best I can do there. Okay, so yeah, the training procedure is just as I explained it. We try to approximate this function of the inputs and also the weights to the function that we have no idea what it is. So that's pretty much it. And why is neural network so popular right now? I mean, it's something that, as I said before, it came to life in the 40s, in the 50s. Why now? Why now this huge effort for building neural network-based solutions? Okay, the idea is that right now, at this moment, we have the hardware that's powerful enough to perform the learning procedure. Okay, the learning procedure, as I said, it's quite simple, but it's a computational, really heavy procedure. Okay, so the idea is that now we have this hugely parallel hardware. I mean, you guys heard of GPUs with hundreds of cores, or even our CPUs with, I don't know, tens of cores. So now we have the computing power to actually make this viable. Okay? So the idea is that you can imagine a neural network as just vector-to-vector operations. I mean, if you go back to the... Yeah, you can imagine these guys here. I have weights here. So I can build a vector with all the weights in all the neurons. Okay? And then the procedure of just making the signal move forward, as I said, we have to sum the input signal and decide whether or not to propagate it. Okay? But just forget the part of propagation. Think about the summing thing. So you have here one vector, and you have here another vector. And you can imagine this forward operation as just a vector-to-vector operation. Okay? That's okay for you to imagine that. But if you do that, you lose parallelization opportunities. I mean, think about this guy as being just one kind of operation, and this guy being another kind of operation. From here, that I don't really have any dependence between these guys. I mean, someone sees a dependence. I mean, the inputs from this guy are not the same as these guys, but actually they come from the sources that we can only expect them to be finished their computation. So if that's the input, this guy just reads the input, this guy reads the input, and this computation is completely independent. So another way to look at this thing is like a vector to a scalar operation. So these guys are completely independent. So for me, it makes sense that, I don't know, processing procedure of this neuron can be performed in one core. The processing procedure of this neuron can be performed in another core. And I can scale this, I don't know, to up to 300 because they can work in parallel. Okay? So this is why now this kind of model is really, really trendy. Okay? So coming back to the decision of whether or not propagating the impulse of the signal, this decision is made by a very specific function. It's called the activation function. And the responsibility of this activation function is to decide whether or not a neuron will propagate the signal or not. Okay? So that's the part of the role of the activation function. And there are quite a few activation functions. Okay? You're gonna, if you read about, read about these guys, which are activation functions, really popular for defining neural networks. Each of them has their own properties, so I'm not gonna go over the properties, but just for you guys to understand that I have to define the behavior of whether or not I'm gonna propagate an impulse. Okay, so I have to have the idea of threshold. I mean, if the value coming from the inputs are this big, then I can propagate this impulse. If not, I won't. Okay? So that's the behavior described in all of these functions. I put the rectified. I put this one in red because it's the most commonly used nowadays. Yeah, but it's no different than the other ones. So it just has some mathematical properties that are really nice for training models. But yeah, let's not go that way. So yes, so this is pretty much the same picture that we had before, with only one addition. Is that of a guy called bias, which means that in our model, if we define our activation function, okay, most of those guys they have they have a really strict behavior. I mean, if you're thinking about, I don't know, go ahead. So if you're looking like a sigmoid function, which looks exactly like this, I mean, it comes from 0, and you have a phase shifting around 0.5. Okay, I'm going to learn these weights here. Okay, the x here is my input. I'm going to learn these weights here. So all of my inputs, I'm going to decide whether or not I'm going to fire when we pass this phase shifting. Well, whether or not I'm going to fire at 0.5 or not. Okay. So, sorry. It's not about 0.5, it's about this phase shifting. So sorry. But you can imagine if my inputs are not really that strong. I mean, I can have negative inputs coming from. Okay, the signal can have a negative value. But if I use something like this, I'm not going to be able to fire the neuron, like never, because it's never going to be higher than 0. Okay, so never. The idea of the bias is just another parameter that we add, and it enables us to move the function. I mean, if I want to decide that my neurons are going to fire in negative values, I can do that using the bias. And that's the bias role in this case. Okay? So just for you guys to understand that there are the weights, I have to figure out the bias, and all of these guys, they are learned during the learning procedure. Okay?
Good morning. My name is Yuri, as Dr. name said too. I work with NCC, like I'm a computer scientist. I started to work with neural nets in 1998. I hold a Master in Science from the Aeronautics Institute of Technology and Brazilian Air Force Institute of Research. And now I'm going to pursuing my PhD in mechanics and aeronautics engineer in Brazil. Detailed collaboration with MIT, and my interest is basically neural nets and DSP, with emphasis in wavelet. Do you know wavelet?
Let's start with DSP.
Digital Signal Processing. Okay, go on, please. In the next few minutes, I will talk about three very interesting models of neural nets: the perceptron, the multi-wave perceptron, and most recently, convolutional nets. Yeah. Have you ever heard about these models? Yes. Perceptron is the older one. It was conceived in 1988 by two scientists from the United States, Frank and Lack. This model was constructed using studies made by other scientists like Macaulay Pitts, who studied the and creating artificial models for the neural mathematical models. Great. Well, perceptron is the simplest model of neural net. This model has a problem that I will speak, and I will talk about this problem in a few minutes. Basically, his net is constructed using only one neuron, as Mr. Rob said.
No, Mr. Please.
No, Mr. Doctor. No, okay. I'm not nervous, but a few minutes is okay. Okay, go back, please. This model is made using this neural net, using single synaptic waves. It's a vector with n parameters. It's a vector in n dimension. Okay, whose components are real numbers. Existed in the original one model of neural nets that these components are complex numbers. But it's not very common. We use today mostly use real numbers. Okay. This model has a basically a step function. Represents a behavior like winner takes all, or else the neuron fire or not fire, right? Depend on the inputs. But we can use to a linear function. Okay, next, please. Well, here we have a simple perceptron. We have two inputs. Yeah. These inputs came from the other neurons or the environment, like an image, like a sound, text, or any kind of information. We have here the knowledge of the net. Here we have the soma, or nucleus, neural nucleus, who's responsible for the dot product, the linear relation between inputs and synapses with or vector waves. Okay. Nice. Here we have now output. What is the output of this? You can see the output as a predict of some response for some like when we saw a car and we understand, oh, it's a car. Our neurons fire response show to us that is a vehicle, not a plane. Okay. Well, we have. Can you understand? It's simple for you. This equation. Okay. We have here dot product. Okay. The linear combination. We have waves and inputs of the neuron. Here we have the impulse, the activation, better, for activation, the sign will be sent to the activation function. It will be a linear, a sigmoid, or a linear function. And then this function will produce the output of neuron, response of the net. Well, we have here a transpose of W. Well, product with X minus a bias. Well, how can we train a perceptron? Perceptron must be taught. Yeah. Sorry, be taught. Okay, but how can we do it? Well, we need to compare the correct output provided by a teacher, by experimental, or what else? Sorry. Okay. Yeah.
So just so you guys know, the output is already defined in your data set.
Yeah.
You have to know the output for learning. Okay.
The output is provided by a person or by a system, but it's a correct response to a problem, Okay. Here we have a predicted response. Then we compare two, subtracting them, and we get error. With this error, we can adjust the waves. How we do? Here we have the knowledge in time t, and here, what else? We send inputs for the neural, it predicts output, we compare to using the correct response and get the error, then we keep this error and use here in this expression to adjust the vector or the vector waves, right? Vectors whose represent the neural of the net. Here we have atom with a learn rate. This parameter determines the velocity, speed of learning, the neural learning. Okay. Here we have input, and here we have the error. We construct an factor, and add this factor with this wave in the previous time. This result will be the next value of the wave. Okay. And in this procedure, the looping procedure, we are adjusting in each epoch, in each period, the waves of the net. We are adapting the new logic of the net, conducting the net to the correct person. Okay. Yes.
Just to put it in another word, the learning rate actually determines how much of influence one learning style has on the next one. Okay, so if I want to really value my previous learning style, the learning rate actually determines the impact of the previous step on the next one. That's pretty much it.
Here we have one problem of the perceptor is that he's not able to classify non-linear problems because the activation function. Yeah, we have a linear function using euro, and this function will construct a hyperplane between two classes. For example, if you have a car, a bus, and a train, and a person, a perceptor, we won't be able to classify these elements. We won't be able to surface to separate these classes correctly. Okay? This problem was discovered by Marvin Minsky, scientist, American scientist, in 1999. And this problem stopped the advanced neural nets for about 20 years. Well, here we have example of non-linear problem, the XOR function. Do you know how it works? XOR, or exclusive OR, is a logic function where the output is one only when one of these inputs. Yes. XOR is exclusive OR. So we have constructed this function using two inputs, x1 and x2, 0, 0, 0, 1, 1, 0, 1, 1. The XOR output will be 0, 0, 0. When only one is active, is on, we have one as an output. And here, 1, 2, and here, 0. Okay? We have all the memory. Okay? No.
The example.
No example. Okay. But the function is correct. Okay? B. It's a simple function, but it's a non-linear function. If we have, let's put in a plane. Here we have x1. Here we have x2. Sorry. That's big here. 0, 0, 1, 1, 0, 1, 1. Okay? Okay. 1, 1, 0, 0. How to separate these classes? For example, the function OR is a linear function. Okay? We have this behavior 0, 0, 0, 1, 1, 0, 1, 1. 0, 0. Okay, 1, 1, 1. Yeah? Here. 0, 0, 1 here. Okay. Yeah. You can construct this hyperplane. Hyperplane is a plane, it's a line in one dimension, a plane is two dimension, and so on. 0, 1, 1. Okay, here, percent. Okay, we solve here. What can we do for solve this problem? We can use for solving. we need a more powerful machine. We need a machine that will be able to build in this space non-linear surfaces. Yeah? And we will get using non-linear functions as activation functions. This is the trick whose conduct us to the multi-layer perception. Have you ever have you heard about this model in multi-layer perception? I mean, there's something that. Okay, what is multi-layer perception? Multi-layer perception simply is a net constructed by many layers, where each layer is composed by a number of neurons, count numbers, 1, 2, 3, and no, we can have a layer with 3, next layer 2, and so on. Yeah, the number of neurons in each layer is independent. Okay. Well, we have a system like this. The output of function, the net, output of net. A net can be seen as a function. Here we have the input, the stimulus. Stimulus, okay? The stimulus from the environment or from the another net. Yeah. I use the net, net for control of Earth-based systems. Like missiles or drones. Okay. Here we have input, function 1, layer 1, or else. Input is passed through layer 1, the outputs of this layer pass through layer 2, pass through layer 3, and outputs. Here we have these 3 outputs, the outputs of the data. Okay? Okay. Now we have nets with very high numbers of layers, which we call it deep neural nets or deep learning. Okay. Go on, please. Here we have an example of the layer perception. Here we have inputs, X and X2. First layer, second layer, third layer, the output layer. Okay. So the design came from the environment, passed through this neuron. This neuron computes using an activation function. This design to this neuron and so on until the last layer, where we have the answer for a problem. For example, here we present a car, and here we have a response. So this is the car. After training, when we present a car, this net will be a response to car. When we present a cat, this net will respond to another car. Okay. You will be able to classify the inputs. Okay. First step is feed forward. In this step, we feed the net. We present the input and get the response. The output. Okay. Next one. Okay. Okay, next one. example of NPL with two phases, forward and back propagation. We have the complete cycle of training. So we have inputs. Here we have outputs. We can have one zero. We have only one input as here, and we have one output two here. Okay? The number here is was estimated was great by us. No. Any number can be any number here. Calm down. Let's go. Before. What happened in before? Can you tell me? For example, we feed forward. What happened in this math? Come on. In feed forward, math is computing. Yeah, it's producing an output. Present. Which, for example, we are computing using an activation function, assign, and in the layer, the output layer, that will produce or show a response for this problem. But in the first step, in that, still it's not trained. That don't know how to cross the street, for example. Someone needs to train it. Okay? Train him, train her. Okay? Here, this phase of back propagation, we will do it. Back propagation, in back propagation, we adjust the waves of the net and model of adapting that will show you to the next slide. One, please. Cool. Yeah. Okay. Yeah, we are short. Sorry about my English because I'm very nervous. Did you understand what I said? Have any questions?
If, for example, when you get an output, you can use that feedback to learn or to teach to the elements, no?
Sure. I'm sorry, I didn't.
For example, I guess the input,
Okay.
and then that data or that information we can use to teach again or to modify that the neurons can decide or compute.
Yes. You use the output to train to adjust the waves of the net. Only layers net. To the last layer until the first layer. This is not the only one model of NPL. We have NPL with recursion, like multi-layer perceptron with recursion in the last layer for the first, or the middle layer for the first. Well, like Elm nets and other nets. Okay. Okay.
Yeah, any more questions? So let's get our hands dirty and try to write some code because I'm fed up with all this talk. So you can see something working really. So yes. As I said, we are going to use Python. We are going to use a really simple Python framework for neural networks. It's called Keras. which is KERKS. Okay, so it delivers an abstraction layer for you that you don't really have to know how the learning procedure works. I mean, you have to understand how it works because you want to use it right. But you don't have to go through all those steps of making those for loops to sum up all of the weights times the inputs and stuff like that. For example, I'm gonna give some look, show you that we cannot build such that for deciding whether this problem here. Okay, so just so you guys know, you cannot draw a straight line that separates the two classes. So I'm gonna try to implement this problem using this framework. Okay. We're gonna use the Chaos framework, and also we're gonna use a second framework called NumPy, which is just a framework for designing matrices in Python. Because I mean, Python is really a beautiful language, but the guys that they didn't really think about HPC at first. So they delivered a language which cannot store a bidimensional data. Okay. You can use it like list of lists, but it's quite different than a two-dimensional matrix. Okay. So we're gonna use these two guys to build that first example, and then you're gonna see how easy it is to get this thing working. So the tool that I'm using is called the Jupyter Notebook, which is an interactive shell that you can run Python commands, and then you get the outputs. And then you go on, and you can also mix this with Markdown syntax. Have you ever heard of Markdown? It's the language that you use at GitHub to write your README files and stuff like that. So it's really nice for making that analysis because you can write between the code. So your code at the end is well documented. So let's start making. I'm going to use Python 3. Then let's just import the framework that we're going to use. So yeah, we imported the framework that we're using. It's called Chaos. Can you guys read this at the back? Can all you guys read this? Is it too small? Should I increase the font? Okay. So yeah. So the first thing that I did was to import the library that we're going to use for building our neural network. Okay. Now I'm going to import the second library so we can define our input. Okay. So I'm going to do it. No, not yet, not yet. Come on, you just follow here. This is for you guys to implement it. Yeah. Don't worry, there will be plenty of time for you to do this. Just adding some documentation. And run it. Okay. Whenever you see this sign here, it means that the command was successfully executed. So, now we define the data set. We're going to call it X. Okay. So what I did so far is to define that table over there, right? Just that combination without the answers. So my inputs are going to be 0, 0, 0, 1, 1, 0, and 1, 1. Okay? Now, adding documentation because it's an input inside variable x. Then we're gonna go ahead and define our output. We're gonna call it y. So the output is gonna be the first. Okay. I'm gonna say the output is gonna be 0, 1, 1, 0. Okay, this is our output. Now I can inspect my variables, just typing the name of the variable and running, and it outputs the result. So yeah, just for us to know that it is right, and do the same with the y variable. Okay. This is our x and our y. Now it's time for us to define our neural network itself. So we are going to use a model that's called sequential, because as Julia explained, we're going to have just the data flowing in one direction. Okay? And the way that Keras works is just like this. You actually stack layers. So you're going to define one layer, the next layer you add to the model is going to be below that one, or if you prefer at the horizontal, it's going to be to the right of the first one. So you're going to build your neural network layer by layer. So I'm going to import the class responsible for defining a model. As I said, it's called sequential. Okay. Now, create the new model. Created a new sequential model. Okay. Guys, if you have any doubts, please stop me at any time. Now I'm going to define my layers. Okay. I'm going to use what we call a dense layer, which actually means that all of its neurons are connected to the layer previously. So it's just like yeah. It's going to draw the idea of what is dense layer. So as you can see, this kind of layer, the layer in the middle, yeah, we call it dense because it's connected to all of the neurons in the previous layer. Okay, so you can see that. So we're gonna create a new dense layer. We're gonna first import what we call dense layer. See, in Python, all of the libraries that I'm using, you have to import them. And if you want to use some function, then you have to import it if that function is defined inside the library. Okay, so I'm just importing the. So I imported the dense layer. Well, I'm going to call it this one the layer 1. Just one thing. Using this framework, you don't have to define the input layer. Okay? You just say, oh, this is the data set I'm going to use it, and it connects the input layer to the. It actually self-defines the input layer and connects to the data set. So you don't have to define the input layer. You just have to say what dimension is your input. So we're going to do that. The first parameter that I'm going to define is the number of outputs of the layer. Okay, as not that drawing, this is 3% simply. For example,
Simple perception.
So the model is like that we're implementing. We have the input from two variables, okay, x1 and x2, and we have a single layer with a single neuron, and it only has one output. So I'm defining that. So I say I'm going to have just one output. I'm going to say what kind of activation I want to use. Okay. For the classic example, I'm going to use a linear activation. Okay. And then I have to define what is the shape of my input. With this, I'm just saying that my input is got like two columns, but whatever the number of lines it is. So it could be as well like this, 2 by 4. Yeah, just like that. Okay?
Sure.
Yes.
Number
Here? Yes, exactly. How, when you define the first layer, it connects like that.
Okay. First these, second.
I'm sorry, I forgot to tell what I'm instantiating. So I'm instantiating a dense layer, and I'm saying I can only have one. I'm gonna only have one output. The activation will be linear, and the input shape is gonna be like 2 columns by 4 lines. Okay. Now, when we use the tests, we need to compile our model. Actually, when we compile the model, that's when we tell what kind of optimization strategy we're going to use to minimize the error. I mean, you guys saw the error is the difference between the value that I'm guessing in the network and the value that I'm supposed to guess, the real value. So I actually get the error from these two values. So when I compile my model, that's when I tell what kind of optimization strategy I have to use to make this error as small as possible. I'm gonna define I'm gonna use the model.compile. Okay. So the error in this framework is called loss. Okay. So they decided to call error loss, but so you have to define some form of loss, and the framework defines a lot of functions for loss. But we're going to use a really common one that's called mean square error, which is just the average of the square of the error. Okay. So we use the square because we want to avoid positive and negative problems. So we're going to use the square. Yeah, let's define it like that.
Mean square error.
Yes. So it's just the error to the square. You sum it up, and then you get the mean. So we call it MSC. You can go more specific. Okay. Now we have to define what kind of optimization strategy we want to use. We're going to use a really common one, which is called the stochastic gradient descendant. I don't think we have enough time to tell you how does it work, but actually it's a way to calculate the minima of a function. Okay, imagine you have a function, and you have to guess what point is the minimum of the function.
Here we have the outcome of vector of waves. Okay?
Yeah.
We can have a very simple function like this.
So you want to find this point over here.
The minimum.
You can imagine if that's this, the weights over the error. You want to minimize the error by changing the value of the weights.
You probably. here we had surface model.
Don't go there. Let's go with the simple case. Okay.
Okay.
Forget this one.
Okay.
So this procedure, it actually tells how do you walk on this line so you can reach this point here. Okay, so that's what we call a gradient, because if we were talking about a function of a single variable, that should be a derivative. Okay? So, but we're talking about multivariate function, so we call it a gradient. Okay. Come on, guys, you are from engineering, you're supposed to know this. So yeah, I'm gonna use the SGT, which is the stochastic gradient descendant. And then I can define some metrics that I'm going to use to tell whether my model is good or not. So a really common one is called accuracy, which actually tells that, well, you are right, like, I don't know, 50% of the time, you are wrong 50% of the time. Okay, so it's like the percentage of the times that you guess it right and the percentage that you guess it wrong. So I'm going to define that. You can actually define quite a few metrics, and the framework has quite a few defined. So, of course, I'm going for the first time. Okay, so I forgot to add my layers to the model. I mean, I defined a layer over here that has just 1 euro. And I said, okay, that's a layer. But I forgot to connect it to the model that I'm training. So we're going to use the add function. So now my model has 1 layer. We can use this function over here to check the summary of a model. And here it says, well, you only have 1 layer, okay? The output of this layer is going to have just 1 value. And the number of parameters that I have to train is 3. Okay? I have the 2 weights and also the bias variable that I told you about. That's the number of variables that I have to train, that I have to guess. Now I'm ready to perform the compilation of my model. Now my model has been converted into a computational graph inside the computer memory. Okay. Now what we do, we have to use the fit function, which is the training function. That is actually the function that's supposed to perform all of those interactions that in this framework are called epochs. Okay? So they perform all these interactions by calculating the error using the mean square error that we define, trying to minimize the error by changing the weights using the stochastic gradient descent. That's what it does. Okay, so we're gonna use the fit function. The thing good about this notebook that actually provides autocomplete. So yeah, you can forget the name of the variables and it tells you what it is. So the first one I'm gonna have to provide is the data set itself, right? So I call it X. Then I have to provide the right answers, which we call it Y. Okay. Now we have to specify some things. We have to define what we call the batch size. What is the batch size? The batch size works like that. How many of the examples that I have, I feed my network before I update my weights? Okay? That is really, really close related to high performance computing. I mean, you can perform quite a few operations in parallel, as I explained to you. And you can perform whole inference in a network in parallel. Because the instructions are really, really, really simple. I mean, you can only see matrix multiplications. It's simple. So you can perform several of these inference. Then you update the weights of your networks based on this batch of inference. Okay, that's what we call it batch size. So this is a parameter that you have to tune when your model is not really fast during the training. The training procedure is taking too long. So I can think about changing the size of this guy according to the amount of memory, amount of the size of my cache, and stuff like that. Okay, for our case, let's just make it as simple as possible. We're gonna say, examine just one example of our data set at a time, and then update the weights. Okay. Now I tell how many epochs I want this model to train, and the number of epochs, as he explained, is the number of times that I'm gonna go through the learning procedures. With some luck, your model will converge in a few epochs. But for some models, actually it takes a lot of time. For some models, they actually don't convert. But there comes a time that you have to stop them and say, enough training, that's good enough for me, or that I have to train some other model. Okay. Let's go with a number like 1,000. That can seem like a lot, but for some really powerful models, you can train them for like 100,000 steps and still not get a good accuracy. So this number, it actually depends on the time that you have to make your solution. So but we're going to go with 1,000. And then the framework does like this. It displays every step of the training. Okay? So this is the step 124 of 100. Oh, sorry, of 1,000. And then at this step, my loss, my error was 0.26, and my accuracy was like 0.5. Or I can only say that it's like tossing a coin in the air. I mean, it has or tails. It makes no difference. So after 1,000 training steps, my accuracy actually dropped to worse than a coin. Okay? Sometimes it happens. I mean, if you train your model for too long, sometimes accuracy drops. Yeah. So that's the accuracy of the model. Now we can evaluate our model to see how good it actually is or is not. But we know it's not, but we can try it. We're going to use a specific function called evaluate. We're going to build a score. Now, we feed them our data set, okay, and the value that we were supposed to guess. That's it. It's gonna build the score, and now we can write our score. So, at our data set, I mean, for the training data set, we got like 0.75. As I said, we cannot, if you want to understand a simple function of an XOR, 0.75 is not, it's not. I mean, if you want to implement it like that. So, yeah, lousy model that works really bad. So, this is the value of the loss that I got training. And I'll play the value of the accuracy of the training. So it's
this result, the perception, is not able to solve nonlinear problems. Yeah. Did you understand?
Even after 1,000 steps, but we can increase that. We can go to over 2,000, 100,000, and another number. Yeah.
Yeah. We never can be able to find the hypersurface to classify these inputs.
So what we do? Well, we have to introduce the nonlinearity function. Okay, we're gonna make a slightly more complicated method. I mean, not that complicated. We're gonna just add another layer with another neuron. So it's not that complicated. And we're gonna use this network. Actually, this is that one that you dropped. Yeah, that one. So it's not that much more complicated than that one. 2 layers. And now I'm gonna show you that it's gonna be able to classify the XOR problem.
It's important to consider that we are using only our functions here, here, and here. Okay?
So how are you gonna do this? Go ahead. Yeah, actually, I have a more complicated example for you guys. That it's gonna be a lot more fun than doing this one. Yeah. So yeah, I'm gonna be quick over this second example, and then you guys are free to perform the test. So I'm gonna be doing the model named model 2. Okay. It's also gonna be a sequential model. Yeah. Now we're ready to add our layers. I'm gonna go straight and define layer 1. That's gonna be a dense layer with output of 2. Okay. The activation. As I said, we have to introduce the nonlinearity of the problem. Okay. So I'm gonna go with a really simple activation function, which is called a sigmoid function, which is not the one that we draw, but it's close to that. That's hyperbolic tangent, right? Yeah. So sigmoid. I'm gonna say that my input shape is the same as the one we defined before. It's the same data set actually. Okay. Define the first layer. Now we're gonna define the output layer, which is the last one. It's gonna be a test with output of 1, activation of also sigmoid. Nonlinearity is important. Okay, define the 2. Now I'm gonna add those 2 to my model. Layer 1, then 2. Sorry, output. Yeah, added those to my model. Now we're gonna see the summary of the model. Check the number of parameters that I have to learn. So this is why training neural network is so hard. Because the number of parameters that you actually have to train, if you add another layer or another set of neurons, it goes exponentially. So it can be really hard to find this amount of parameters. The one that you're gonna build in the example, for you to programming, you got to be like, I don't know, 1,000 parameters or something like that. Yeah. Now, as before, we have to do a compilation of our model. As before, just gonna copy that. Copy it before. Yes.
Yes, I'm listening. Are you using a logis or
Logis. So, loss is gonna be mean square error. The matrix that I'm gonna use again, it will be heuristics. Thank you. In the optimizer, it will be the same as GD. Okay, so now let's just change the way the network works by adding another layer with some extra neurons. And now we're performing the same before. 6 parameters. 2, 3, 4, 6. 6. Yeah. We compile our model. We have to perform the feed.
We need 2 bytes there, isn't it?
Yeah.
So it's 9.
super variance plus 3?
So I define that I'm going to use the same data set, the same answers that I had before. Okay. Now, define the batch size. It's going to be 1 again. And the number of epochs is going to be 2,000. How much we use? Okay. Let's go with 2,000. Yeah. So, yeah, this is going to be quite shocking because our network cannot yet identify the XOR. So, yeah, it's going to be a small framework problem that I have to explain to you guys what happens, and then we're going to be able to do one that actually works. So, let's go with the score. Evaluated as X5. Score. So sorry, just 1 second. This one should be model 2, right? I'm performing the fit again in model 1, so we'll define it model 2. So let's go to training again. So you can see that our model is really not going that well because you see the loss is like the same in most of the interactions, and the accuracy is not really that good. The thing is that you remember the drawing that we make with when you want to calculate the mean, right? So it starts right here, and we move toward the mean. The thing is that this is a really simple abstraction of the thing. We have a highly dimensional space to look for the optimization. So this thing here is not two-dimensional. It's not, yeah, it's highly dimensional. So if you imagine that we were at a three-dimensional space, the learning procedure actually works by, I don't know, if it was a person, the learning procedure, you cannot imagine how amazing that would be. It's like you're walking towards the meaning. So the learning procedure is this path that you walk towards the meaning. But sometimes your model gets stuck at a region, okay, what we call a plateau. So it just walks in circles and never leaves the region. And there are quite a few techniques that you can use to avoid this. One is, I can actually take larger steps. Okay, maybe I get out of the plateau. And I also can use some statistics. I don't know what to call it. It's witchcraft. It's statistics witchcraft. Yeah. Now we don't have time to go over that. So one of these variables that we use really often is called momentum. Okay. So we are gonna adjust right now the learning rate, the size of the steps that I'm gonna use, and also the momentum.
Regularization is another hyperparameter that we use to avoid overfitting, for example.
So how we do that? Those are parameters that we actually define in our optimizer. So if we're using the statistical gradient descent, we have to tune this optimizer with these parameters. So I'm gonna do like this. I'm gonna have to instantiate a version of this stochastic gradient descent with my parameters, with my learning rate and also my momentum. We call learning rate the parameters called LR. Sorry, we're going to use a learning rate of 0.1. A really huge learning rate for most of the case.
We usually use 0.05, 0.01.
Yeah. So we instantiate our optimizer. Now we're gonna use it here. We're not gonna use the default optimizer, stochastic gradient descent. We're gonna use ours. We rectify the model. Now we're ready to perform the feeding operation again. And with some luck, we're gonna see going to accuracy of 1. Yeah, I'm counting on luck.
You still put SGD.
Yeah, I use this one, which is this one.
Okay.
Speed of the learning depends on
So for
to the
2,000 steps, no deal. Maybe we can try with 5,000 steps or stuff like that. I swear I tried in my notebook this morning and it converted in less than 2,000. But again, we're dealing with well, stochastic process. So you can only tell that yeah, sometimes they converge in a few steps, sometimes they don't. But still.
it depends on the initial point of the vector in space. Sometimes we get a good initial solution that help us for rapid conversion to the solution.
So, but yeah, you can take my words. It actually worked. No, actually, I had it here. It worked best. Yeah. I don't know what went wrong with my. No idea what's happening. Actually, we went to a learning rate with the smaller values.
Yeah, I think these steps are to be
Yeah. Which would be the base.
smaller steps.
Let's try with this one. Yeah, actually, this one's. I think so. So it's not well. So sorry, guys. It was supposed to work, but yeah, you got the feeling of how the framework works, and now it's time for us to do some programming. I mean, we still have 1 hour left. It's supposed to go to work. Okay, so first of all, we're gonna return to our computers. I'm gonna show you how we start this environment and how we get started with using it for programming. So yeah, first of all, I want all of you guys, everybody, everybody's okay with the computer, everybody's got it. So yeah, everybody, log into your machines. Okay, I want you guys to go to a website called, you can type in Google, Miniconda. Just go. The best part is that it's super jump. It's okay. For you guys, you can use the internet at your computers? No.
Well, most of the time there are some other
Anyone can use the internet. Then go over this and download the software for Linux, which is called Zonda 3 for Python 3.6. Okay. So it's going to be really small, so it won't take a lot of time to download. So everybody downloaded? Nobody downloaded? Yeah, I clicked that link like 5 minutes ago. Okay, it works. So in this one here, okay, it's the 64-bit version bash installer for Linux. You're all gonna click it, and then you're gonna open a terminal, right? To open a terminal, you go over here and you just type terminal. Then you're gonna have a window like this. Okay? I'm just gonna increase the font size so you guys can see. Yeah. Everybody can see this? Great, okay. So just one question, everybody downloaded. The next step we have to install it. Okay. Come on guys, talk with me please.
Yes.
It's already.
It's already live.
It's allowed.
It's downloaded, okay?
Yeah.
So it's supposed to be in the descargas. Okay. So you have this file here. Conda 3 latest Linux x85 x86. Sorry. So yeah, in order to install this thing, you have to run it's an executable. It's an installer. So to run this, you type bash and the name of the file. Yep.
Yeah, it's the best guys.
Okay. Yeah, because actually you have to change the permission to execute those bash. Yeah. Just bash. No problem at all. Okay. Please don't. Yeah, so you should use your own. Well, I actually never used the function. No, I actually just used it. It's really, really nice. It works really good. So guys, now you hit enter. Yes. And then it's gonna ask you for confirmation that you want to install it and that you actually review the license. And I swear to you that the license is really good. You're not gonna sell your soul. I mean, not right now, but maybe later. Then you have to type. You go to the license, and you type yes. I want to install it. Okay. Okay. Then it's gonna ask you where do you want to install it. That's the good thing about the mini conda thing. The mini conda is a software for managing Python virtual environments. So if you want to have like several Python installations in your system, this is the way to go. Because we're going to do that. We're going to use this package manager and also virtual environment to create a virtual environment that's not going to affect the system. It's not going to affect the Python installation of the system. Okay? And you can do it in user space, which is really good. But you don't have to have like the sudo access, root access, and stuff like that. You don't have to be the super user. In your home, it's okay. Just type enter. No. And then it's going to install like lots of software. And at the end, what it does is it creates a few, especially the one called condas, CONDA. It's the one that we are going to use. Here, it's asking you, should I alter your path so you can use the conda command? And you have to say, yes, please do. Okay. The installation is finished. What we do now is that we close this terminal and we open another one so that our changes can take. So we're going to close it and open again. Now, you guys must have the command line named conda. You guys okay? You okay? How about you? Okay. You? Yes. Okay. I'll be honest. I used this for testing. But the installation works. I mean, 100% of the time it works. So, everybody okay with installation? So yeah, now we're going to create a new environment. So this is one of the parts that actually the HPC knowledge comes in place. We're going to use not the standard versions of the Python libraries. We're going to use Python libraries, optimize it for this architecture that we're using. Here they are Intel-based computers. What Intel does, it has specific versions that work better with their hardware. So we're going to install the versions of these packages that are optimized for this specific hardware. So when somebody asks you, where do Python and HPC meet, this is the place. I mean, you're going to use very highly optimized libraries for a specific architecture. For GPUs, you have the same. use libraries that are optimized for GPUs, unless you want to program in CUDA, which I don't recommend. Yeah, so in order to create an environment, what you need to do, you say, for instance, I want to create an environment, then you use the parameter where you specify the name of your environment. You can give whatever the name you want, as long as it doesn't have space. Okay, so we're gonna create one called. Is it okay? Please don't type enter yet. Don't hit enter. Yeah, please don't hit enter. I'm not finished. So yeah, we're gonna create an environment named WorkShop, which they call. Okay, now we say, please download the software from the Intel repository. Okay, we do that using the -c command line. And now everything that you download, it will first try using Intel repository, and then it will use the default chain. If it's not available, if it hasn't been made available by Intel. Now, we specify the version of Python that we want our environment to have. So we're going to go with Python 3. Okay? Now, you can hit enter. What this command does, it actually creates an environment with a specific version of Python downloaded from Intel. So this version is optimized for Intel architectures. Okay, everybody got the same screen? Come on, guys. If you're not, please let me know and I'll walk you through.
E60 was already installed there, so it's already
Okay. Problem. So yeah, everybody creating. So yeah. Yes. You can go ahead. Yes, it's okay. Yeah. It says that you cannot upload anything from here, so I guess it's an issue. But you can see her and watch the steps. You can go through the section. So everybody, okay? Yes. So it downloads the Intel Python version, okay? Then the Python version, the Python, which is this is some bindings from Intel to their libraries that are optimized for Intel architecture. It goes like that. If the internet continues to work to finish. Well, any of you guys could do that? It worked for you? Yeah, but for me. So yeah, let me start it again.
No?
Okay, let me just create mine again and see if it works. So what is going to happen? So it seems like it's working. So you should be don't worry, it is installed. Yeah, you can actually do it. Yeah, everybody? Created environment? So yeah, created the environment. Now we have to activate the environment. And how we do that? It actually tells you how to do that. So this is the line here: source, activate, and the name of the environment. Okay? That. So yeah, if you do that, then you hit enter. Then you are inside the virtual environment. Okay? So whatever you do here, it doesn't affect the system. And you can do whatever you want. You can install new versions of Python. You can remove the version of Python that you use. You can install new libraries. It's not going to affect the system. Okay? How do I know that it actually works? I'm going to ask. Yes. Which? Yeah. I'm going to ask which Python am I using? Yeah. And it's going to answer this Python here, which is a binary, a Python binary, which is installed inside your home folder.
Python or Python 3.6?
No, actually, Python 3.6, point to this one. You can use that. Yeah. From now on, whenever you are inside this environment, you only have one Python. And a Anaconda doesn't really allow you to create, to put two Pythons in the same environment. So whenever you ask for Python, it's gonna insert the Python that you send it to install. So you can forget to write Python 3.6 or something like that. You can just type Python. Everybody?
Yes.
Python installed. Now we're gonna use. We have to install a few libraries. I mean, I talked to you about the Keras library, the NumPy library. We're gonna install a few libraries in order to execute the Python notebook, so you guys can start working and then, yeah. We do it using the conda install command. Okay. Once you're inside the environment, you're gonna see that your prompt changed. So the name of the environment goes here. Okay. Everybody's seeing this here. Okay. So you're gonna go and install conda install. Again, we're gonna say, please install the software optimized for Intel architecture. Okay? And now we specify which libraries we want to install. So they're gonna go to with NumPy. Okay? Keras. Another one that you're gonna use, it's called Matplotlib, it's for plotting. Okay? Drawing. And I specify this one. And the thing is that Keras actually works on top of a library called TensorFlow. I mean, it's a Google library. I think some of you guys have heard of it. It's a really good library for machine learning, but it is a low-level library. So in order to define a neural network, you have to specify which function you're going to minimize and how you're going to minimize it. So it's not like this that you say, I want this layer, then train it for me. You have to be more explicit than that. So Keras work on top of TensorFlow. So we have to install this library too. TensorFlow. Then we have to add the Jupyter notebook that we are using, that graphical interface that allows us to write Python code and then run it iteratively. So, some libraries that we're going to use for our example. Okay? Everybody? Yeah. Okay, so you can hit enter. And now it's going to look for lots of packages because it's not going to only download the libraries that you said, but it's going to download the dependencies. So this is where this tool really helps. I mean, in a normal environment, you have to install all of these dependencies so you can use a library. But this kind of package manager helps you install all the dependencies. And actually, this environment dependencies tool actually helps you to manage dependencies outside Python. I mean, if you are using like mathematical libraries like LAPACK Plus or something like that, this tool actually can download these libraries and make it available for your installation. So you don't have to worry about downloading OpenGlass, for instance, and then compiling it and making it and linking it together with your Python libraries. This tool does that for you. So yes, and as you can see, it's downloading OpenMP. It's downloaded the Intel MKL library, which is the mathematical kernel library from Intel, that kernel library from Intel, which provides optimized versions of class and LAPACK operations for Intel architecture. So stuff like the dot product between two matrices, it's highly optimized inside this library. So what Keter does, it actually tells TensorFlow to use the dot operation, and TensorFlow uses the MKL operation, which is implemented in C. So this is the point where I tell you that using Python has a good performance for doing neural nets. The hardcore operations are done by C. Okay? And most of these implementations are already parallel. So you're going to use all of your cores, it's going to use all of the vector instructions that you have and stuff like that. I don't know why it's downloaded twice, but so it's going to take a little because we're building like a really big environment, but we're doing with 3 lines so far. So so anybody finished? So this is what is good about this environment. You can do it in your house, in your machine, in your notebook. It's not a problem. It's really lightweight, and it uses the hardware that you have available. So yeah. So once I'm giving you the tasks for the hands-on, I'm really sure that you're not going to be able to finish it here. So you can do it at home. Actually, I'm giving you both the answers for the tasks and also the tasks, so you can finish at home and write me if you have any questions or doubts or something like that. So everybody finished but mine, right?
You're not lucky today.
Yeah, no, not at all. So yeah, for you guys that finished, now I'm going to ask you to go to this website. Which is So yeah, go to this website. This is the place where we store all of our hands-on activities, not just in Python, but also the ones that we're gonna be doing in C in the afternoon. So yeah, the first one is the books, the Python notebooks containing the instructions for the hands-on. Okay? You can open it. WorkShop to this down. In order to download, you can find the button here that download. Okay? You can, if you are familiar with it, you can get the clone command working, and then you can clone the. You can also perform the download as zip file, and then you uncompress it. Yeah. So in this repository, you have two Python notebooks. Okay, the one is called MNIST NLP. MNIST is a well-known data set for digit recognition, where you have 60,000 samples of images that store digits, handwritten digits. I mean, they got like 7, 6, and stuff like that, handwritten. And then you have the class to which those digits they belong to. I mean, here you're gonna say it's a 6, here you're gonna say it's a 7, but sometimes you have something like this. What is that? No idea. Your neural network is supposed to tell the difference. Okay? So yeah, the first one, I'm gonna open it. Everybody could download it. Yes. Mine's not finished yet. Okay, so the first one is this one. Okay. Now you see, it's supposed to be self-paced. I mean, you guys are supposed to be able to do it just by yourself without any help. There are quite a few explanations about what everything is. Okay. So the first step is to load the dataset. For this, you have a helper function that actually makes the split between the dataset that you're going to use for training on neural networks and the dataset that you're going to use for testing. Okay, so it does all that at once. Yeah. Then we have the definition of the neural network itself. I mean, the first one, it's a really basic one, really basic neural network, which only has 2 neurons for the first hidden layer, and then you have an output layer with 10 outputs, okay? Which is what we call one-hot encoding for the output. So you actually encode your output using binary code. So if it is a 1, you have 10 neurons at the output layer, okay? You have 10. If it is a 0, then you're gonna have something like this. 0, sorry. Yeah, 0, and then all of the bits are gonna be 0. If you have a 1, so it's a 0, 1, 2, up to 9. Okay? If you have 9, then it's gonna be 0, 0, 0, 0, 0, and you have 1 here. So this is what we call one-hot encoding. It's a pretty normal thing to do with neural network because well, in neural, it's not going to say it's a 6, it's a 5. It's going to say to which that input belongs to. So here, it's saying that it belongs to the first class. Here, it says it belongs to the 10th class. Okay, so the neural network is quite simple. Yeah, here we use the same techniques for training our model that we use here. We use the mean square envelope and also the descent for optimization. Okay, and then at the end, I have a few tasks that I ask you guys to do. The first one is to build a dummy classifier, because I mean, you're going to train this network. This network is a fully functional network, but it's a really bad one. I mean, the accuracy level is like 11%. So it's worse than saying random numbers. Okay? So the first one, just to warm up in Python, you're going to build a dummy classifier. Which just throws a dice and says, well, it's a 1, it's a 2, and checks whether it's for making new predictions. Okay? So yeah, but you're already familiar with Python. The second one, I tell you guys, well, neural networks are really good when you're able to normalize your data. The normalization process is the one that you're going to use to place your inputs, your input values, in a value between 0 and 1. Okay? So if you're dealing with small value, you're going to save lots of memories and stuff like that. So working with normalized data is quite common. So the second task, I ask you guys to normalize data. And actually, that's a quite simple step, because you can see the digits. They are encoded just in in grayscale. So you have values from 0 to 2, so 256 values. So the normalization problem, if you have values from 0 to 255, let's just divide it by. Okay. And the third one is really the challenge. This is the good one. You can skip the first two and go straight to this one. And actually has few tasks that you guys are supposed to perform. Check the results of making those changes at your model. I mean, the accuracy level is supposed to float up. Sometimes it will go down, but at the end, you're gonna go from 11% to 98%. Okay? And it's gonna be simple for you guys. Let me just check if mine finished. Wow. Yeah. So I'll just get the repository here. Okay, so now I have all the files that you guys have. Yes. So you guys are supposed to have these files, right? In order to start the Jupyter notebook, you just have to type Jupyter notebook. Okay? And once you've done that, hit enter. Okay. Then type Jupyter notebook. Yes, right. Jupyter notebook. Yes. Then enter. And then it's supposed to open your browser. Okay? In the same directory that we were when we typed the Jupyter notebook command. Everybody got the same here? Okay? Nope. Yeah, where do you know the
Yes.
yeah,
It was the fault. So it's okay.
okay, let's see where you so it's gonna be at this here. Okay. Yes, here. Start here. Wherever you want.
I would like to put it in.
Where? Inside the
Yeah.
that different fiber just covers the the installation process of Python. So you don't have to worry where to put it. You can put it anywhere you want. Okay, yes. Do that.
So
Yes, it's gonna download it there and do that. So you see inside it. So you see you have sorry. Sorry, I keep typing that Spanish keyboard, so yeah. Pull this thing out. Yes, so there. And now you try to. So you download it.
Yeah, now.
Now extract it. Yeah,
documents.
Let's start the. Yeah. So it's inside the mini folder here, then documents inside documents. Now you try to notebook and it gets right. It's gonna be the right.
Yes.
So yeah, you see what are the requirements here. So see how the things are. Here, here, this environment. Everybody, we're on the same page here. Okay, now let's click at this, not go here, not the answers. I mean, you're not gonna cheat in front of me. Let's go with the exercise first. So yeah, here is the same file that we were looking before, but this one here, as I explained it to you, has not been executed, right? You saw when I was typing the comments during the demo that every time I executed what they call a box of code, then you have a number here, which corresponds to execution sequence number. Okay? So if I execute this box first, this is going to be 1. If I execute this one, this is going to be 1. And then if I execute this, this is going to be 2. It's just the sequence in which those comments will run. So yeah, each box of this is a box of Python executable code. Okay? So what you guys are going to do first, we're going to run all of these boxes. Okay? And how do we run a box? We have a sign here, which is play button or something like that, that executed just one box. Okay? If you want to execute all of them, you can go to cell and they say run cells. Okay, so they don't call box, they call it cell, but yeah, it's pretty much the same. So if you do that, whenever a box is running, you're gonna see a little star at the in between the square brackets. Okay, it's gonna take a while for running the first time because it actually is loading lots of stuff. So yeah, give it a time, give it some time for. Yes. Sorry, you were supposed to run all, not run cell. Run all. So sorry. Yes, so now you can see it's supposed to be running all of them. So it actually downloads the dataset by itself. You don't need to worry about how you're going to download it. Now, then, we just randomly draw some samples from the dataset just to take a look at it and see what it looks like. So this is our inputs. So this is typically how our inputs look. as I said, handwritten digits encoded in grayscale. Okay? Then he's gonna declare the network, compile the model, and train, and you're gonna see a really bad accuracy. Okay? You can see 20%. As I said, it was not 11%, but it's 20, it's still crap. Okay? Then we're gonna plot some predictions. I mean, we're gonna use our network to predict what this is. And our network says that this is a 1. Okay? This is a 8. This is an 8. We can clearly see that it's an 8. Here, it is a 5. And it also says that it's 1. So that's why yes, but actually sometimes we got different values. But why is that? Because our model is really, really bad. Perhaps it says, well, 99% of the time, maybe sometimes it says something else. But that's exactly what is wrong with our model. It's really, really bad. Okay? So yeah, I also say so, but it's because the model is really, really bad. I mean, you're gonna change that during the assignments in the problem. So yeah, so if you guys want to jump straight to the third one, feel free to. That's gonna be easier for you to do. So the first one is to increase the number of neurons at the first, at the layer that we defined. We had like 2, you're gonna increase it to 128. Okay? If you have any doubt, please raise your hand over there, Julia over there.
Okay, everybody. Do it.
So guys, you already have the answer, so you have still 10 minutes, but let me just give a few words. Just thank you guys for attending to our session, which is really nice. I mean, you have, I'm gonna make available these slides and also all this material you already have. It's all public, it's on GitHub. And you can actually contact us using our GitHub account, no problem. And just to thank you guys for being here. And any feedback is really, really appreciated.
Thanks to you. It was very nice.
Okay, thank you a lot. Você assim desse. Ela vem toda de baixo. Passou. Eu queria ver se eu. Então, eu acho que o seu carro é o carro. É isso que eu tô pensando. A gente. Abraço. Yeah, let's do it. Yes, exactly. Sorry, yeah. Just like this thing is interactive. So whenever you do an add, you're going to the model that you define at the step. What you really need to do, right, is to kind of hit restart. Okay? Then it's gonna remove everything from memory. Then you go run all, and it will run everything again. Then you're gonna see the right. Because as I said, it's imperative. So the model variable that you declared before, and constantly new layers. So that's what is the yeah, it's true. But I was slow there. This hit yes, I know. But what we this is the part that we actually couldn't talk about. The dropout is a method that we use for avoiding, it's a regularization technique that you actually use to avoid graffiti. Graffiti is the phenomenon where your model performs really, really good in your training data, but it's really, really bad in your test data. So you have like a bias or so dropout actually does it randomly at a rate of 0.25 off the synapses between the neurons. So during the training, for a specific layer, you have a 25% chance here. So when you do that, you force your little map some other paths for making the same field. So that is really, really good for dealing with overfit. So I'm really sorry that we couldn't talk about it for the time. Or between two days later. Yes. Discarding 25% of the output of this layer. Yes. True, but just doing trades.
May I ask you an unrelated question? You say you are storing more than 2 petabytes, almost 2 petabytes.
Yes.
But you said that the communication channel is not a problem. You said about 100 gigabytes.
Yeah, we're going to 400 right now.
Download two. That's fine.
Yeah. The thing is that the dataset download, they are made as schedules. I mean, it's not always that every researcher is looking for the same dataset.
It's not coming out.
No.
Real time.
No. It doesn't come like 2 petabytes at once. It comes from like 5 gigabytes 500 gigabytes at once. Because some physicists want to make some experiment, some simulation, and it needs a specific data set that's stored at the tier 1. So it downloads this data set to all. So whenever someone says, well, I need to work with this data set, you have two choices. You can work in a local cluster, or you can look for clusters around the world that already have this data set. So yeah, that's how it works. No, we can't download like 2 petabytes of data twice.
No, not difficult questions. You told us that you are working with dark energy and dark matter. Do you have some
Actually, I've been working with Hungarian collider. Just that, there's a phenomenon called boosted jet separation. Whenever you have a process that you collide, you have like these jets of particles, and then you have to separate the jets and tell what kind of particles this is and what kind of, because you don't actually collide just 2 protons or something like that. You collide like 30 at a time. So you have to separate which, what kind of jets come from which collision. So we've been working right now.
Great.
But it's exciting, but the physics, because physics is not my background, so for me, it's Yes. Yeah. It's better if you go in this other.
It's just I don't this one here
Instead of the mean square. Yes.
but I was before this one.
No. This is one.
Yeah.
You can start with that one if you want to. Yeah.
And this one.
Just duplicate this one. Yeah, you just erase this stuff. Check because it's not the first layer, it's the second one, so you don't have to worry about the import. So you just put it before.
That and then you
Yes, exactly.
And
the dropout, yes, the one that you can see. So sorry that we talk about. Yeah. In between both that you.
And
Instead of means right there, it will be categorized plus central. And then the RMS props, you're going to replace SGT with that. No, actually, for classification problems, this one can be used mostly for number estimation, regression problems. This works better for regression. And the other one, it's another optimizing mechanism, which is based on the stochastic gradient, but it has some small changes. And I think the paper in there, it's not that simple to understand. As you can see, the framework is supposed to hide all the complexity. And it's just, come on, use this format and use this.
Why is the cascade more than the initial configuration? What is the cascade?
How do you initialize it, right?
That's the only cascade.
Yes. Yes. No. RMS probe, really know what it's intended for, but it's another type of for calculating the gradients, and it's faster than the stochastic. Yeah, but actually, yes, it helps avoiding those settle points that I said. So you reach a plateau when you start working a certain thing. So you go much faster to the market. Good, it's we can go to session.
Okay.
So guys, again, thank you very much.
Thank you very much.
Thank you.
Thank you very much to Dr. Méndez de Oliveira.
The slides? Yes.
Yeah, I'll make them available somewhere. But yeah, I'll tell them where it's available. Perhaps if they don't comment first. Go finish round.
Okay, that's what I'm saying.
Thank you very much to Dr. Méndez de Oliveira. Muchas gracias a ustedes, muchas gracias a los doctores de INTEC que nos han acompañado. Les agradecemos su paciencia haber estado acá. En la tarde, después del almuerzo, continuaremos con WorkShop on Hybrid SPI OpenMP, Programming for Intel Platforms, a las 30 de. Muchas gracias por su asistencia, muchas gracias.